Welcome everyone. An outline of Day2 FDP contains semaphore, problems using semaphore, deadlock, problems on deadlock, deadlock avoidance, problems on deadlock avoidance. Before seeing semaphore, we need to know what is meant by independent process and cooperating process. Independent process does not share any file, variables or databases, whereas cooperating processes share files, variables and databases. Process synchronization is a technique to coordinate the processes that use shared data. And coming to race condition, it is the condition where several processes try to access the resources and modify the shared data concurrently, and this race condition leads to data inconsistency. And this race condition can be avoided by using a technique called process synchronization. Process synchronization is mainly used for cooperating processes, and it is a technique to coordinate the processes that use shared data. Coming to critical section, it is the part in which only one process is allowed to enter and modify the shared data, and this part of the process ensures that no other process can access the shared data. So these are all the prerequisites we need to know before getting into semaphore. Coming to semaphore, semaphore is a kernel resource, or we can say that it's a synchronization tool that provides synchronization. We can say semaphore is a variable that is used to solve critical section problem and to achieve process synchronization in multiprocessing environment. Semaphore can be accessed through two atomic operations called wait and signal. Wait is denoted by P and signal is denoted by V. Atomic operation is an operation that is executed in a single CPU time slice. Preemption is not at all possible while executing an atomic operation. And coming to semaphores, there are two types called counting semaphore and binary semaphore. Counting semaphore, its value can range over an unrestricted domain. It is used to control access to a resource that has multiple instances. Then binary semaphore, it has two values 0 and 1, and always its value is initialized to 1. It is also used to implement solution of critical section problem with multiple processes. Let us see a problem using semaphore. A counting semaphore S is initialized to 10. 4 V operations are performed on S. We need to find the final value. We already know P as wait operation. P usually decrements the value of semaphore by 1, and V signal operation increments the value of semaphore variable by 1. We need to find the final value of semaphore. So final value is equal to, already S is initialized to 10. So here it is 10 plus the signal operation usually increments the value of semaphore variable by 1. So here 4 V operations are performed. So it can be written as 4 into 1. Then wait operation decrements the value by 1, and here there are 6 wait operations. So it can be written as minus 6 into 1. This is equal to 10 plus 4 into 1 is 4, minus 6 into 1 is 6, which is equal to 8. So this is the final value of the semaphore S. Let us see next problem. Here the counting semaphore was initialized to 7, 20p operations and x v operations were completed on this semaphore. If the final value is 5, then what will be the value of x? And the options were given. S is equal to S is initialized to 7. So S is equal to 7 initially. Then P wait operations, that is 20p operations are performed. Wait operations decrement the value, so it will be minus 20. Then X signal operations were performed. So signal operations increment the value by 1. So it will be x into 1, that is nothing but x. So here S is equal to 7 minus 20 is minus 13 plus x. The statement given in the problem is final value of semaphore is 5. So it can be written as S is equal to 5. From these two equations, since both the left hand sides are equal, we can equate the right hand sides. So minus 13 plus x will be equal to 5. So x is equal to 5. Minus 13 goes to the right hand side, so it becomes plus 13. This is equal to 18. So the value of x will be 18. Next, let us see about deadlock. Deadlock is a situation where execution of two or more processes is blocked because each process holds some resource and it waits for another resource held by some other process. And this situation is called as deadlock. Let us see this example. In this example, P1 holds the resource R1 and waits for resource R2. R2 is held by process P2. Process P2 holds R2 and it waits for R1. R1 is held by P1. None of these two processes can complete and release the resource. Thus both the processes keep waiting infinitely, and this condition is known as deadlock. Coming to the necessary conditions for a deadlock, the first thing is mutual exclusion. It means that there must exist at least one resource in the system which can be used by only one process at a time. If another process requests that resource, the requesting process has to be delayed until the resource has been released. And printer is an example for mutual exclusion. Second necessary condition is hold and wait. It means there exists a process which holds some resources and waits for another resources held by some other process. No preemption means once a resource has been allocated to a process, it cannot be preempted. Circular wait means all the process must wait for a resource in a cyclic manner. Coming to this diagram, P1 waits for the resource held by P2, P2 waits for the resource held by P3, P3 waits for the resource held by P4, and P4 waits for the resource held by P1. So this is an example for circular wait, and all these four conditions must hold simultaneously for the occurrence of deadlock. If any of these conditions fail, then the system can be ensured deadlock free. Coming to the formula used here, maximum number of units of R that ensures deadlock equal to sum of maximum needs of all processes minus total number of processes. that is sigma xi minus n. Sigma xi is sum of maximum needs of all processes. N denotes total number of processes. Then minimum number of units of R that ensures no deadlock is equal to maximum number of units of R that ensures deadlock plus 1. That is sigma xi minus n plus 1. So these are all the two different formulae we are going to use for solving the problem. Here in the given problem, a system is having 3 user processes, each requiring 2 units of R. What is the minimum number of units of R such that no deadlock will occur? Let us use the formula. Here how many processes are available means 3 processes. Let us name them as P1, P2 and P3. The maximum need of each process is 2. So P1 needs maximum 2 units, P2 needs 2 units of resource, then P3 needs 2. We need to find the sum of maximum needs. So here the sum will be 2 plus 2 is 4, 4 plus 2 is 6. So coming to the problem, here it is 6 minus total number of processes. Total number of processes are 3. So 6 minus 3 will be equal to 3. We need to find minimum number of units of R that ensures no deadlock. So that is equal to maximum number of units that ensures deadlock plus 1. Already we have found maximum number of units that ensures deadlock. It is 3 plus 1 is equal to 4. So the answer for the given problem is 4. Next problem. A system is having 10 user processes, each requiring 3 units of R. What would be the minimum number of units of R such that no deadlock will occur? Let us name the 10 processes as P1, P2, P3 etc. up to P10. Each user process requires 3 units of R at the maximum. So P1 needs 3 units, P2 needs 3 units, similarly P3, P4, P5, P6 up to P10. Every process requires 3 units at the maximum. So if we find the sum, the sum will be 30. So here we will write as 30 minus total number of processes is equal to 10, because there are 10 user processes. 30 minus 10 is equal to 20. We need to find the minimum number of units of R that ensures no deadlock. This is equal to maximum number of units of R that ensures deadlock. We have computed that as 20 plus 1. This is equal to 21. So this is the answer for the given problem. Next problem. A system is having 3 user processes P1, P2, P3, where P1 requires 21 units of R, P2 requires 31 units, P3 requires 41 units. What is the minimum number of units of R that ensures no deadlock? From the given problem, P1 requires 21 units of R, P2 needs 31 units of R, P3 needs 41 units of R. We need to find the sum of maximum needs of all the processes. So if we find the sum, the value will be 93 will be the sum of maximum needs of all the processes. So here it can be written as 93 minus total number of processes. There are 3 user processes. So here it will be minus 3. This is equal to 90. Next we need to find minimum number of units of R that ensures no deadlock, that is equal to 90 plus 1. This is equal to 91. So this is the answer for the given problem. Let us see deadlock avoidance. Banker's algorithm is used in deadlock avoidance. A state is safe if the system can allocate resources to each process in some order and still avoids a deadlock. A system is in a safe state only if there exists a safe sequence. A safe state is not a deadlocked state. Conversely, a deadlocked state is an unsafe state. Not all unsafe states are deadlock. However, an unsafe state may lead to a deadlock. From the given diagram, a safe state is not a deadlocked state. Conversely, a deadlocked state is an unsafe state. And not all unsafe states are deadlocks. However, an unsafe state may lead to a deadlock. In Banker's algorithm, here we assume n to be number of processes and m as number of resources. And the following is the algorithm for finding whether the system is in safe state or not. Here we take 2 vectors, work and finish. The length of work is m and the length of finish is n. M denotes number of resources and n denotes number of processes. We initialize work is equal to available. Then we make finish of I as false for all I is equal to 0, 1, 2, etc. up to n processes. That is, we make finish of process P0 as false, then finish of process P1 as false. Likewise, for all the processes in the system, we initialize finish of I as false. Next, we need to find an I such that finish of I must be false and need of I must be less than or equal to work. Both the conditions must get satisfied. If no such I exists, then we go to step 4. Suppose if both conditions are true, then we find work. Work is equal to work plus allocation of I. Then we make finish of I as true. And again we go to step 2. That is, we next proceed for I is equal to 1, I is equal to 2, etc. up to I is equal to n. And finally, if finish of I becomes true for all I values, then we say that the system is in a safe state. Coming to resource request algorithm, here we find request of I is less than or equal to need of I. If this condition is true, then we go to step 2. Otherwise, an error condition is raised since the process has exceeded its maximum claim. Coming to step 2, we find request I less than or equal to available. Suppose if that is true, we go to step 3. Otherwise, PI must wait since the resources are not available. In step 3, we pretend that the requested resources are allocated to the processes by modifying the state as follows. That is, available equal to available minus request I, allocation is equal to allocation plus request, need equal to need minus request. So we compute all the 3 things. In this problem, a system with 5 processes P0 through P4 and 3 resources of type A, B, C are given. Resource type A has 10 instances, B 5 and C has 7 instances. So this is the given tabular column is the snapshot taken at time T0. We need to find the content of need matrix. Need is equal to maximum minus allocation. That is, need is a vector. Maximum is also considered as a vector unit. Then allocation is also considered as a vector unit. We perform vector subtraction here. Now the content of need matrix will be for process P0, so maximum minus allocation, 7 minus 0 is 7. Then 5 minus 1 will be 4. 3 minus 0 is 3. Then for process P1, three minus 2 will be 1. 2 minus 0 is 2. Then 2 minus 0 is 2. For process P2, nine minus 3 is 6. 0 minus 0 is 0. 2 minus 2 is 0. For P3, two minus 2 is 0. 2 minus 1 is 1. Then 2 minus 1 is 1 again. For process P4, if we compute need, we have 4 minus 0, which is 4. Then 3 minus 0 is 3. Then 3 minus 2 is 1. This is the content of need matrix for the given snapshot of the system. Here let us compute the total in the allocation. 7 from resource type A has been allocated. 2 from resource type B has been allocated. Then 5 from resource C type has been allocated. Available is equal to total minus allocated. Already the total resource type of A is given as 10. Then B is given as 5 and C is given as 7. minus the allocation vector is taken as 7, 2 and 5. So the final value will be 3, 3, 7 minus 5 is 2. So this is taken in available 3, 3, 2. Next problem, we need to find if the system is in safe state. Suppose if the system is in safe state, then we need to find the safe sequence. So this is the content of the system. Let me get out with the algorithm here. See, this is the algorithm for checking whether the system is in safe state or not. Work and finish are vectors of length m and n. We need to initialize work is equal to available, and we need to make finish of I is equal to false for all I values. Here m is equal to 3 because there are 3 resource types A, B, C. Then n is equal to 5 because there are 5 processes P0, P1, P2, P3 and P4. In the first step, we need to initialize work is equal to available. So work is equal to, the content of the available vector is 3, 3, 2. Next, we need to make finish of I as false for all I values. So we make finish of 0, finish of 1, finish of 2, finish of 3 and finish of 4 as false here. Here we initialize the value as false for all I. Step 2, we need to find an I such that both the conditions must satisfy. Finish of I must be false, the need of I must be less than or equal to work. So for I is equal to 0, finish of 0 is false. Need of I is nothing but need of process 0. Need of process 0 is 743 from the above table. We need to check whether this is less than or equal to work. The value for work vector is 3, 3, 2. 7 is greater than 3, 4 is greater than 3, 3 is greater than 2. So this condition becomes false. Hence, P0 must wait Next, let us take the value of IS1. Finish of 1 is equal to false. Next, we need to find need value. Need of 1 is 1, 2, 2 from the above table. So this is less than or equal to 3, 3, 2. 1 is less than 3, 2 is less than 3, 2 is equal to 2. So the condition is true. So both the conditions are true. F of 1 is false and need of 1 less than or equal to work. So both the conditions are true. Therefore, we proceed to step 3. Work is equal to work plus allocation. This is equal to work is 332 plus allocation for P1 is, from the above table, the allocation vector for P1 is 2, 0, 0. So if we make vector addition, it becomes 5. 3 plus 2 becomes 5. Then 3 plus 0 is 3. 2 plus 0 is 2. So this is the new work value. Next thing, we make finish of IS true. That is, finish of 1 must be made true. Next, I becomes 2. Finish of 2 equal to false. The need of 2 is, from the above table, the need vector for process 2 is 6, 0, 0. We need to check whether this is less than or equal to work value. So new work value is 5, 3, 2. 6 is greater than 5, whereas 0 is less than 3, 0 is less than 2. But the condition is false since 6 is greater than 5. So process P1 must wait. Process P2 must wait. Here it is I, not 1. Next, we need to find for I is equal to 3. Finish of 3 is false. Need of 3 is, from the table, the need vector value for process 3 is 0, 1, 1. We need to check whether this is less than or equal to 5, 3, 2. Zero is less than 5, 1 is less than 3, 1 is less than 2. So the condition becomes true. Therefore, we can compute new work value. New work is equal to work plus allocation, that is 5, 3, 2 plus the allocation vector value for process 3 is 2, 1, 1. So this will be equal to 7, 4, 3. After finding new work value, we need to make finish of I is equal to true. That is, finish of 3 must be made as true. Already finish of 1 is true, so P1 is in safe state. Now finish of 3 is true, therefore P3 will be in safe state. Next, let us compute for I is equal to 4. Finish of 4 is equal to false. Need of 4. Need vector value for process 4 is 4, 3, 1. We need to check whether this is less than or equal to new work value, that is 7, 4, 3. 4 is less than 7, 3 is less than 4, 1 is less than 3. So the condition is true. Finish of 4 is equal to false, as well as need of 4 is less than or equal to work. So we can compute new work value, which is equal to vector 7, 4, 3 plus 0, 0, 2. This is equal to 7, 4, 5. Now we need to make finish of 4 as true. Finish of 4 must be made true. Now process P4 can be included in the safe state. Again we have to work for I is equal to 0. Now finish of 0 is equal to false. Need 0. Need vector value for process 0 is 7, 4, 3 from the table. We need to check whether this is less than or equal to work. Now the work vector value is 7, 4, 5. 7 is equal to 7, 4 is equal to 4, 3 is less than 5. So the condition is true. Finish of 0 is equal to false. Need 0 less than or equal to work. Both the conditions are true. Now we have to compute work. Work is equal to vector 745 plus allocation for process P0 is 0, 1, 0. This is equal to 7, 5, 5. Now after computing work value, we need to make finish of 0 as true. Now we can include P0 in safe state. Still finish of P2 is false. Now let us compute for I is equal to 2. Finish of 2 is false. Then need 2 is, for process 2 the need vector value is 600. This must be less than or equal to work value. Work is 7, 5, 5. Six is less than 7, 0 is less than 5, then 0 is less than 5. So the condition is true. Now compute work. Work is equal to 755 plus allocation. Allocation for P2 is, allocation vector value is 302. This is equal to 10, 5, 10, 5, 7. Now make finish of 2 as true. Here all the finish values have become true. So coming to the last step, since finish of I is equal to true for all I, the system is in safe state. And here P2 will be added at the last. So this is the safe sequence P1, P3, P4, P0, P2. The system is in safe state. What will happen if process P1 requests one additional instance of resource type A and two instances of resource type C? This is the snapshot of the given system. Let us get the resource request algorithm here. First, P1 has requested, it has requested one additional instance of resource A. Then no B, hence it is taken as 0. Then two instances of resource type C. So it is taken as 2 there. The request made by process P1 is given as vector 102. So first step is we need to check whether request of P1 is less than need value of P1. So request of P1 is 102. We need to check whether this is less than or equal to need. Need is 1, 2, 2. 1 is equal to 2, 0 less than 2, 2 is equal to 2. So this is true. Hence we go to step 2. In step 2, we need to find whether request of process 1 is less than or equal to available. So again we check 1 or 2 less than or equal to available. Available vector value is 3, 3, 2. 1 is less than 3, 0 is less than 3, 2 is equal to 2. So this condition is true. If condition 2 is true, then we proceed to third condition. In the third condition, we assume the resources have been allocated and we compute the following. First we compute available. Available is equal to available minus request. 332 minus request made by P1 is 1, 0, 2. So this will be equal to 3 minus 1 is 2, 3 minus 0 is 3, 2 minus 2 is 0. So the value of available vector will be 2, 3, 0. Next thing we need to find allocation of P1. Allocation of P1 is equal to allocation. The allocation vector value is 2, 0, 0 from the above table plus request. The request value is 1, 0, 2. So this is equal to 3, 0, 2. And the last one we have to find is need value, need vector value of process 1. So need is equal to need I minus request I. That is need vector value of process 1 minus request vector value of process 1. That is 1, 2, 2 minus request vector value is 1, 0, 2. This is equal to 0, 2, 0, 2, 0. So this is the value of need vector for process P1. For the given problem, we have executed resource request algorithm and we have found allocation vector value for P1, need vector value for P1, and finally we have found the new available vector value. Since one additional instance of resource type A and 2 instances of C has been allocated for P1, we need to find if the new system is in safe state or not. So we apply safety algorithm. Here M is 3 and N is equal to 5. M is 3 because there are 3 resource types A, B, C. N equal to 5 because there are 5 different processes. Now work is equal to 2, 3, 0. The new available vector is assigned to work. Next we need to initialize finish of I is equal to false for all I values. So from I is equal to 0 to 4, we initialize finish value as false. When I is equal to 0, finish of 0 is equal to false, we compute need 0. Need 0 is 743 from the table. we find whether that is less than or equal to 230. It's false. So P naught must wait. I is equal to 1. Finish of I is false. Then 0 to 0 is less than 230. This is true. Therefore, P1 is in safe sequence and we compute work value. Work is 230 plus 302, which is equal to 532, and we make finish of 1 as true. Then I equal to 2, finish of 2 is false, then need of 2 is less than or equal to work. Work is 532. This is false. Therefore, P2 must wait. Now we take I as 3. Finish of 3 is taken as false. Then need 3. Need 3 is 0, 1, 1. It's less than or equal to work vector 532. This is true. Therefore, P3 is in safe sequence. Compute work now. The new work value will be 743 and we make finish of 3 is as true. Then for I is equal to 4, we compute whether need is less than work. That is 431 less than 743 is true. Therefore, P4 is in safe sequence and we find the work value as 745 and we make finish of 4 as true. Again we compute for I is equal to 0 because P0 is waiting. Here finish of 0 is taken as false. Need of 0 is 743. We check whether that is less than or equal to 745. It's true. Therefore, P0 is in safe sequence. Now, the new work value will be 755 and we now make finish of 0 as true. For I equal to 2, finish of 2 is taken as false. Then need 2 is less than or equal to work. That is 600 is less than 755 is true. Therefore, P2 is in safe sequence. We compute new work value as 1057 and we make finish of 0 as true. So now, that is not a finish of 0, it's finish of 2 because we have computed for I is equal to 2 in the last step. Now the safe sequence is P1, P3, P4, P0 and P2. This is the safe sequence. Since we get a safe sequence, the request for process P1 is granted. That's all for today's FDP. Thank you all.